So good morning, everyone. Welcome back. We will have now Mohammad Altakach speaking about quantum information, CP measurements, and Higgs total at future lepton colliders.
So, thank you. Yes, I'm going to speak about quantum information and spin measurements in Higgs 2 tau at Future Lepton Collider. Priyanka Lamba was supposed to give this talk. Unfortunately, she couldn't make it, so here we go. This work was done in collaboration with Fabio, Kentaro Mawatari, and Kazuki. So since we are still in the morning, I will go slow. So my introduction will be as a warm-up. So some things you will see you already saw before, but I mean, it's better so I don't get injured. So in classical mechanics, as we all know, the angular momentum takes continuous numbers. But as we saw in experiment, spins are actually quantized. And again, so since the beginning of this workshop, Alice and Bob are working with us, so doing their experiment, measuring spin components. We have a spin zero particle. We have Alice and Bob in a space like, in a space separate places, receiving a spin half particle. So Alice is receiving alpha and Bob receiving beta. And so they are measuring the same spin component, the z component, and they say that 50% of the time they are getting plus and 50% of the time are getting minus, but the result is 100% uncorrelated. So what's going on? One explanation would be what we call the hidden variable theory. So in this explanation, the states of alpha and beta depends on a hidden variable called lambda, and 50% of the time lambda will be here, and 50% of the time will be here, and if it's here, then we will have the state of alpha being up and the state of beta being down, and vice versa. And so this completely explain what's happening. However, in quantum mechanics, in this definition, particles have definite properties before the measurement, and this is realism. And Alice's measurement does not affect Bob's outcome, so it is locality. However, in quantum mechanics, the state that explains this is shown here, where here we see the states of alpha, and here is the beta state, and the outcome actually is not determined until we do the experiment. So this is called non-realism, as opposite to the hidden variable theory. And only when someone does the experiment, then the state collapses into either this state or this. So Bob's outcome is determined and is affected by Alice's measurement, and this is non-locality. So we have two explanations of the same phenomenon. So in general, the state would be like this. And if it's separable, then the measuring beta will only affect beta and not alpha, and vice versa. And as we saw in quantum mechanics, it's not the case. So how do we test this? Bell managed to find a way of measuring this, and he also managed to have his name on a street, as we already know now. So it goes in this way. We have now Alice and Bob again, but this time they are measuring different spin components. At the first, so we have 4 samples, 4 experiments. The first one would be Alice measuring spin A component, and Bob a spin B component, and then they repeat this with different axes. And finally, we get this RCHSH, which proved to be bounded by 1 in case of hidden variable theories. But so if you go to quantum mechanics again, it can be easily shown that the spin component is equal to the direction, the unitary vector of the direction of the spin of the axis, and then by taking A and A prime perpendicular and B prime perpendicular, and this B prime is tilted by 45 degrees with respect to A prime, we can find that this R is equal to square root 2, which violates the hidden variable theory. So we have a way to discriminate between quantum mechanics and hidden variable theories. And so let me talk also about spin half particle system. And so for this, we'll introduce, it was already introduced in previous talks, so the density operator, which is written in this form, and the density matrix should satisfy those conditions. Hermitian, should be Hermitian, trace equal 1, and positive definite. And then we can calculate the expectation of our observables using the trace of the observable times the density matrix. And in our spin half particle system, the basis would be those four bases. And then the density matrix can be written in this form, where BI, BI bar, and Cij are real numbers. And then one can see and prove that BI and BI bar are actually the spin I component of particle alpha and beta, and Cij is the spin correlation. And so we would like to actually calculate this. And so in entangled states, so if the state is separable, then the density matrix operator can be written in this form, and also it holds, if we take only the transpose of the density matrix of the beta particle. And so if we can prove that this has negative eigenvalues, then we can say that the state is entangled, and it was proven that this can be achieved by only proving this. So again, if we calculate the C's, we can prove entanglement. And so let's go now to Higgs to tau tau. Let me first show the generic interaction, Lagrangian, and it depends. Sorry, the mouse. Yeah, and so it depends on kappa and delta, and in the standard model, kappa would be equal to 1 and delta equal to 0. And so one can easily calculate the density matrix, and it takes this form, and then BI bar would be equal to 0, and this is the Cij matrix, and then entanglement is 2 cosine 2 delta plus 1. Okay, so we know that we want to actually estimate Cij's in order to be able to test the Bell inequality and also the entanglement. But so to do this, we are dealing with Higgs to tau tau, and so we have a particle that decays, and our detector will not see the tau, so we need to reconstruct it. So let me explain a little bit here. So we suppose that we have a spin half particle that decays to a daughter particle. We call it L alpha and something else. And so we know that the decay distribution is proportional to 1 plus the spin analyzing power times the unit vector of the daughter particle measured in the rest frame of the mother particle alpha. And for two particles, the spin correlation actually will take this form. So in order to be able to have the C matrix, we need to measure at our colliders the unit unit direction vector of the daughter particles, but in the mother's rest frame. And so that's why actually we go to lepton colliders, because taus are light, so they are boosted. So it's like any reconstruction would be huge. So it will be difficult to reconstruct if we don't know the beam, for example, the resolution in a good accuracy. And also in lepton colliders, we have way smaller background compared to the large hadron collider. So as benchmark points, benchmark scenarios, let's say, we take the ILC and the FCC-EE. And we see already here that the resolution is way better for the beams in FCC-EE. And we use MATGRAPH to actually generate standard model events for this process. Okay, and we take into account the effects of the detector simply by just smearing the true energies of the particles, the visible ones. And we perform 100 pseudo experiments in order to estimate the statistical uncertainties. Okay, so And now we want to, as I said, reconstruct the momenta of the taus, and we have neutrinos, and neutrinos, this means we have 6 unknowns, and so we need 6 constraints in order to be able to calculate them. And so we do that using the mass shell conditions and the energy momentum conservation. And then once we have reconstructed the tau momentum, we go to the Higgs rest frame, go to the helicity basis, and then boost our pions to the tau rest frame and calculate the CIJs. And voila, it fails. So yeah, we are supposed to have 1, 1, -1 diagonal, and we have even like flipped signs, and it's not even 1. And also we don't get good results for entanglement and the RCH-SH. And this is actually due to the fact that, as I said, we have smeared energies, and when we are trying to reconstruct a small error, because of the fact that we are boosting, it will have a big impact. And so in order to be able to correct this smearing, like to go back to the correct energies, we use the information about the impact parameter. So I feel that I'm repeating what you said already yesterday, more or less, in the discussion. So we use the impact parameter, and then using this information, we can now accurately have reconstruct the tau momenta, and once this is done, now we move again to the helicity frame. We boost the pions, and we do our calculation, and this time we get those results, which is, as we can see now, is in a good agreement with the standard model values. However, we see that the Bayes inequality could not be really tested at ILC, and as I said, this is due to the poor beam resolution, more or less, in the ILC compared to the FCCEE. Okay, I'm going fast, that's fine. Okay, so now we also, as a byproduct of what we did, we can do a CP test. We saw the C matrix. Now if we take an object A that is formed using the non-diagonal components of the C matrix, if A is positive, then we have a CP violation. If it's equal to 0, then it's consistent with standard model. And we get the results that are in agreement with the absence of the CP violation using what we got here. And so by using the fact that A can be written in this form, we can have the bounds on the delta that are comparable to what was found in other studies. Okay, I was super fast, that's fine. You have more time for questions. So to summarize, high energy tests of entanglements and Bayes inequality has attracted a lot of people. That's why you're here. And we investigated if it's possible to do this at ILC and FCC in the Higgs to tau case. And we saw that it's crucial actually to use the impact parameter in order to be able to reconstruct the tau momentum. And then we showed also as a byproduct of our study that one can have a CP phase test. So thank you very much.
Thanks, Mohammad, for the nice talk. Are there any questions?
Thank you very much. I actually just want to understand a bit better your final results. So maybe can you go back? Yeah, yes, no, one more further? Yes. So maybe I missed something, but what's the dominant effect for your errors here for when you compare between ILC and FCC? I thought was a systematic error.
This is only statistics. Actually.
Only statistics?
Yeah, we did 100 pseudo experiment and calculated the statistical errors.
But before you were saying that your main error was due to the reconstruction, right?
Sorry?
Before you were telling us that your main error was due to the reconstruction.
So I was saying that the fact that I'm not, it's not that. So I showed these results, and I showed those results. And it's not with the errors, it's with the actual value, and this is due to the reconstruction, because we are not reconstructing good enough our taus without using the impact parameter, and that's why we got these results. So if you, for example, check the first one, it should be 1 minus 0.6. And the statistical error is still more or less the same. So it's really the value.
Okay, maybe we can talk later. Okay, thank you.
I have a similar question. The resolutions that you take into account for ZH-associated production is 3% on all the particles, including the jets from the Z decay?
Yes.
Okay. And the uncertainties that you quote in these tables, these are for 100 pseudo experiments. They're not related to the luminosity. Why is this? I mean, your numbers would be way more convincing to experimentalists if you would actually normalize them to integrated luminosity.
Right. I mean, we include by luminosity, you mean the number of events we include. So each experiment we have has a specific number of events based on also the luminosity. Is this what you mean?
Yeah, so the uncertainties, the statistical uncertainties in your tables for the spin correlation matrix C, they are based then on 385 events for the ILC and 666 for the FCCEE, and then still you get 20% uncertainty.
Yes.
Okay. Okay, I'm a bit surprised that the sign of some of your C matrix elements flip when you just add the transverse impact parameters.
Yeah.
That's quite large effect. We don't see, I mean, like I don't see this in the study that I did for Bell 2, and also we don't see this in CMS.
Yeah, so when we reconstructed, here you would get actually two solutions, right?
So it's the sign of picking the wrong solution. How do you pick it if you don't use the transverse impact parameter? You take both, or?
We take both, yes.
Okay, yeah, that can be a large effect. Thank you.
Any other questions? Yeah, I actually have a question myself. So, if I understood correctly, if you don't boost, or if you boost, you completely destroy the entanglement that you had. So you flip completely, right? You had something like a negative value, and when you boosted, you really get.
No, you boost in both cases. It's the tau, and you need to reconstruct the momentum, so you need to go back to the tau rest frame. And because you have boosted, the tau is light, and you are boosting the tau, so the effect of the missed reconstruction would be bigger because of this. And it's in both cases, but it's dealt with in the other case by taking into account the impact parameter.
But the boost itself, does it change?
No.
It's just per se?
No, it's I mean, like your taus are boosted in both cases.
Okay.
It's the same scenario, but we add another constraints in the correct analysis, if you want to call it correct
So you
analysis.
see kind of like frame independent, the entanglement is frame independent in the way when you boost from one to the other.
I don't understand.
Like, yeah, the fact of the boost per se doesn't change the entanglement. It's just due to missed reconstruction.
Yes.
Okay.
And this missed reconstruction would have more impact because of the boost.
Okay. Any other questions? If not, let's thank Mohammad again.